everybody, I'm Tall.
And I'm Small.
And today we're doing Khan Academy's MCAT Prep Biomolecules, Krebs cycle, and oxidative phosphorylation questions. Krebs cycle being the citric acid cycle. Okay, first question. How many molecules of acetyl-CoA, an acetyl group attached to a coenzyme A, are produced from a single molecule of glucose for participation in the Krebs cycle? And that's the citric acid cycle. Answer choices are 1, 4, 3, or 2. Okay, I do not even remember what the citric acid cycle is.
Okay.
I think it makes electron carriers like FADH and NADH. Mm-hmm. Is there any other purpose to it?
It regenerates oxaloacetate, which is really useful, but it's really useful for that cycle specifically, and then maybe creating some amino acids. So not a whole lot of big takeaways from it. But yeah, those big electron carriers that let us do the ETC later on. Okay,
so metabolism-wise, it's really, I guess the main takeaway is it's electron carriers.
Yeah, there's about 10 ATP equivalents by the time you add up all the FADH2 and NADH plus the 1 GTP that's produced from the cycle.
That's right. Okay, so apparently in the Krebs cycle, you use molecules of acetyl-CoA.
Do you know where we get acetyl-CoA from?
Oh no, you produce it. Wait. Oh, you produce it from glucose.
Uh-huh.
So glucose goes in.
Yeah. So the first step of breaking down glucose is
phosphorylating it.
That is literally the first step of the first step. So glycolysis, right?
Oh yeah. Oh, okay. Yeah.
I'm trying big picture. I'm sorry. I should have specified.
Yes, glycolysis.
Yes.
Breaks it down into 2 pyruvates.
Right, pyruvate. How many carbons do we have?
3.
Muy bien. And then starting with acetyl-CoA, do you know how many carbons are in acetyl-CoA?
Well, acetyl means that there's going to be 2 carbons attached to something.
Perfect.
The coenzyme A, because I know that you can
ignore CoA. Every time you see CoA, just know it's a really long molecule.
Oh.
Yeah, and it's like it is shortened to CoA, and it like doesn't cross membranes and things like that. So ignore the CoA.
Okay, so I would not know how many.
So anyway, what I was trying to get you to see is that we start with glucose, which is 6 carbons, right? And then that carbon trick that you mentioned is really, really helpful. So I like thinking about, okay, I start with 6, and then I make 2 3-carbon molecules. Mm-hmm. And then to start Krebs cycle, or the citric acid cycle, or the tricarboxylic acid cycle, then I need 2 things. I need oxaloacetate, which is a 4-carbon molecule, and it's highly oxidized. And then I need an acetyl-CoA. And then my first step is for those 2 things to come together and make a 6-carbon molecule. So by necessity, that acetyl-CoA, and we know from its name, is 2 carbons. So we get that directly from pyruvate.
Okay.
So we go from 3 to 2.
Right.
Because that's the easiest way to get there.
Okay. So how many molecules of acetyl-CoA are produced from a single molecule of glucose for participation in the Krebs cycle? Acetyl-CoA is 2?
Yeah.
So we would have 3 total.
No.
Darn.
Okay, so we have 1 glucose. We end glycolysis with 2 pyruvates, and then each of those pyruvates gets turned into an acetyl-CoA.
Oh,
from pyruvate dehydrogenase, which is in a really cool enzyme. It's so cool.
So 2.
Yes.
2 acetyl-CoAs, because we start with glycolysis that breaks it down into 2 pyruvates. Both of those pyruvates can be turned into acetyl-CoA. Mm-hmm. But this is for participation in the Krebs cycle.
Yep.
It works the same. Glycolysis is a part of the Krebs cycle?
It feeds directly into it.
Okay.
So if we have oxygen and everything is running like it's supposed to, we don't have a buildup of something that would end up stopping this pathway, we would continue going from glycolysis to Krebs cycle to ETC, and it would be like a continuous thing that's being pulled down all the way by that really strong electron drawing factor of the O2 at the end of ETC. Okay, so it should be 2, and that's correct. I'm going to look at those hints real quick, though, to see if it helps me understand this a little bit more. I know I talked a big circle around it. I'm sorry, but it is technically a huge circle. Right. Okay, acetyl-CoA is formed from pyruvate in the mitochondria. Okay, so you have glycolysis happen. It makes pyruvate.
that makes then acetyl-CoA. CO2 is a product of acetyl-CoA formation. Acetyl groups contain 2 carbons. Got it? Pyruvate is a 3-carbon molecule. 2 molecules of pyruvate are produced per molecule via glycolysis. Yeah, we knew that. So 2 molecules of acetyl-CoA are produced from a single molecule of glucose for participation in Krebs cycle. Okay, yeah, so it's exactly what you just said. All right, next question. How are electrons extracted from the citric acid cycle for use in the electron transport chain? Reduction of ATP and GTP, reduction of NAD plus and FAD, oxidation of ATP and GTP, or oxidation of NAD plus and FAD. So, me not knowing any of this stuff,
Yep.
I would immediately remember that reduction is gain in electrons and oxidation is loss. So, if we're trying to extract, I'm assuming it's like when you look at these biochemical pathways and you see like an arrow and then you have a little arrow curling off and it says like NADH or something like that. That's what they're talking about.
Yep.
Like extracting electrons that way. So, if we reduced something, we're gaining electrons. We want something to be reduced so that we can then use it as an electron carrier. And I'm looking at reduction of NAD plus and FAD, and I know that those are electron carriers. Am I thinking the right way?
Exactly.
Okay, so it should be reduction of NAD plus and FAD.
Yep.
And it's right. You got it. Onward. Thanks, Con. Okay, next question. High cellular concentrations of what molecule would inhibit the entry of pyruvate into the citric acid cycle? AMP, coenzyme A, NADH, or pyruvate? Is this like a Le Chatelier's thing?
In a way, yes.
Okay.
So there's a good theme in metabolism that if you have a lot of products building up, you're going to turn off a pathway, that whole negative feedback thing. It makes intrinsic sense. But some of these are like not all enzymes are turned off by their products.
So despite what you just said, I think from the citric acid cycle, the only thing I know that it produces, I believe, is NADH.
Yes.
So if we got a buildup of NADH, we might not be utilizing pyruvate for the citric acid cycle.
Yeah. So I think what I said was misleading. And I just wanted it to be kind of like a cautionary statement that this doesn't always happen for all enzymes. But yes, that is the correct theme to go with.
Okay, you can't always rely on it. However, it's a good guess if you're in a situation like I would be in here.
Yep, yeah.
So I choose NADH, and it's right. Very
So
cool.
Going through glycolysis in the citric acid cycle, something that would push us through, AMP, okay, so I'm lacking ATP, I need more energy, I need to go through oxidative phosphorylation, all 3 steps.
Ooh, so in that case, if we have a lot of AMP, and if you just think about the cell like it's always sensing something, if it senses a lot of AMP, then it knows that it needs to do the citric acid cycle to produce NADH, which would then go to complex 1 of the electron transport chain and make more ATP. Oh my gosh.
I am watching the face of an aha moment. And this is what happens in metabolism oftentimes. You start stringing it together, and this is the reason for this is the reason for this. And then sometimes when people ask you a question, you go through a really long explanation because in your head, that's how things are linked now.
Right. Very cool.
It's exciting.
Yeah. All right. Okay, so next question.
Also,
go on.
Sorry, real quick. Pyruvate, if we have a buildup of pyruvate, what do you think that would do to the Krebs cycle?
It would, I would think it would kick it into high gear.
If we had enough oxaloacetate present to keep doing it, we would just keep generating it.
Okay.
Until we had too much, and too much ATP does eventually turn off some of those important, I think, glycolytic enzymes. So
Okay.
I think hexokinase is a good bet. No. PFK1, phosphofructokinase 1, is one that's pretty highly regulated.
Okay. All right. Very cool. Question number 4. What powers the ATP synthase rotary motor? So what makes the ATP synthase go? Is it CAMP, coenzyme motive force, GTP hydrolysis, or proton gradient? This seems a bit too easy. I believe it's proton gradient.
If you got it wrong, the test center would actually fling you out of the chair.
It's an ejection seat.
Yeah.
All right, so proton gradient, yeah, that's the whole point of the electron transport chain, is like moving electrons through so that you can activate complexes that create a proton gradient.
Yeah, and we talked about they will ask you specific questions that differ in oxidative phosphorylation, this whole big idea, questions that are specifically about the electron movement and questions that are specifically about the proton gradient.
Yeah.
So they do work together, but they have different, answers for those questions, like what is driving the ETC forward as far as electron movement goes. That would be, the O2 wanting to get reduced.
Yeah. It's not the proton gradient that's driving the electrons to move.
It's a byproduct.
Exactly.
Yeah.
It's reducing it's reducing that oxygen at the end.
Yep.
That is cool. Okay. Next question number 5. Relative to FADH2, at what energy state does NADH enter the electron transport chain? NADH enters the electron transport chain at a lower energy state than FADH2. NADH enters the electron transport chain at the same energy state as FADH2. The energy state at which NADH enters the electron transport chain cannot be predicted, or NADH enters the electron transport chain at a higher energy state than FADH2. I think it can be predicted. I think we know it, so I'm going to rule that one out. I know that NADH goes into the electron transport chain at complex 1, so I would just assume that that's a lower energy state, because it just feels like the highest is maybe when you reduce oxygen. So I would say that NADH enters at a lower energy state than FADH2. Do you have any thoughts about this?
Yeah, energy state to me is like favorableness kind of, and going towards the electrons moving towards oxygen feels right. I don't know if that makes any sense to me, but that feels like a lower energy state. So it almost feels like NADH would enter at a higher energy state. But I am totally spitballing because I have no idea. I have not heard this phrasing as far as this question goes.
You pick higher, I'll pick lower.
Okay.
And let's check it. Oh no. Oh, you got it right.
Okay.
Okay, it was higher. So let's look at those hints. Upon entering the electron transport chain, NADH and FADH2 each fall in a stepwise manner from higher energy states to lower energy states. Okay, so NADH, FADH each fall in a stepwise manner from higher energy state to lower energy state. Okay, that makes sense. Entering at a higher energy state implies that a molecule has a higher potential energy and more energy can be extracted from it. So that means that if NADH is at the highest energy state in transferring its electrons in complex 1, then it has the highest potential energy, so more electrons can be extracted from it. Okay.
Yeah, so we learned in biochem that, FADH2 can make 1.5 ATP and the NADH can make 2.5 ATP, but the MCAT and the companies associated with it would like you to kind of round and say that NADH can produce 3 molecules of ATP and FADH2 can produce 2.
Easier math.
Yeah.
When you don't have a calculator, I guess. 3 molecules of ATP can be produced per molecule of NADH via the electron transport chain and oxidative phosphorylation. Only 2 molecules of ATP. Okay, so that's what we just said. So NADH enters at a higher energy state than FADH2. Okay, so you're going from a higher to a lower, and you can think about like it's becoming more favorable. NADH produces more, so higher energy state, more energy can be pulled from it, which is electrons. Therefore, that's why NADH can pull more protons through than FADH. It's a good way of thinking about it, I guess.
Yeah, because complex 1 does really pull those protons through as well, and we can get more energy out of it. So yeah, that does make sense.
Okay. All right, next question. What cellular conditions favor increased activity of the electron transport chain and oxidative phosphorylation? Low oxygen concentrations, low NADH concentrations, high ADP concentrations, high NAD plus concentrations. Okay, so low oxygen, that would be the opposite, because Oxygen is the end of the electron transport chain, the thing driving the movement of electrons. NADH provides the electrons, so we want that to be high for increased activity. NAD plus concentrations, that would just drive the formation of NADH, I think. So maybe the citric acid cycle.
I'm looking at the one that you saved for last, I think strategically.
Yes.
That is denoting that our cell is lacking some energy.
Yeah, if we have high ADP concentrations, we've been using all of our ATP, and we need to phosphorylate that stuff. So that's going to help to drive the electron transport chain, and oxidative phosphorylation, which would phosphorylate an ADP into ATP.
Yep, I think you are doing a wonderful job with picking up on these overall themes that are really just so important for metabolism.
Yeah. Yeah, you really can just kind of like gestalt your way through.
Oh no.
To use a psych-soc word.
Cringe.
All right, so next question. With respect to their relative pH, how do the cytosol, intermembrane space of the mitochondria, and the mitochondrial matrix compare? So we're talking about the relative pH, cytosol, intermembrane, and then inside the mitochondrial matrix. pH of the mitochondrial matrix is less than the pH of the cytosol, which equals the pH of the intermembrane space. The pH of the intermembrane space is less than the pH of the mitochondrial matrix, which is less than the pH of the cytosol. The pH of the mitochondrial matrix is greater than the pH of the cytosol, which is greater than the pH of the intermembrane space, or the pH of the cytosol is greater than the pH of the intermembrane space, which equals the pH of the mitochondrial matrix. So the intermembrane space is going to be the highest, I think. Because that's where they're getting pumped. Well, it doesn't depend on what point in the cycle.
Yeah, I was thinking the opposite. I was thinking it would be the lowest because we would have the highest number of hydroxide or hydronium.
Ooh, but the fact that so I'm thinking about the sodium potassium ATPase.
Yeah.
You have to use energy to pump the ions against their gradient.
Yep, both of them.
So we have to use energy in the ETC to pump hydrogen ions supposedly against their gradient, right? Meaning maybe there's a higher concentration in the intermembrane space.
You mean in the matrix?
There's a higher concentration in the intermembrane space than the matrix.
Yeah, okay.
If we have to use energy to pump them through.
Yeah. Okay.
So maybe I think intermembrane space is the lowest pH.
Yep.
And then I would say the mitochondrial matrix, that's where all these ions are coming from. I would say that's next. And then the highest pH would be the cytosol, because I think the cytosol operates close to physiological pH. So I would pick that. And I would be wrong.
Yeah. So I was with you on the pH of the intermembrane space being the lowest, having the highest number of hydroxide ions. I don't know how to reason out the other two. I just simply don't.
Okay, so the correct answer is the pH of the mitochondrial matrix is higher than the pH of the cytosol, which is higher than the pH of the intermembrane space. So we were right about the intermembrane space. Let's look at their hints to see what they've got to say. All right, ATP synthase in the inner mitochondrial membrane is powered by the proton motive force. The proton motive force is due to the concentration gradient of hydrogen ions between the intermembrane space and the mitochondrial matrix. The hydrogen ions move down their concentration gradient from the intermembrane space to the matrix. Therefore, the concentration must be higher in the intermembrane space, and thus the pH of the intermembrane space must be lower. So we reasoned out that if a significant gradient existed between the cytosol and the intermembrane space, it would destroy the gradient between the intermembrane space and the matrix. Oh, so the cytosol and the intermembrane space are relatively similar.
Okay.
Therefore, it doesn't destroy the gradient.
There's not much change back and forth.
Right. There's no like real strong gradient to try to pull the protons out.
Okay.
Okay. Although it is more permeable than the inner membrane, the outer membrane of the mitochondria is not permeable to all ions or solutes, so it cannot be considered continuous with the cytosol. In reality, the pH of the cytosol ranges 7 to 7.4, near neutral, is much less acidic than the intermembrane space of the mitochondria. What? That's not making sense. The pH of the hold on. What are we missing here? If a significant gradient existed between the cytosol and the intermembrane space, it would destroy the gradient between the intermembrane space and the matrix. Okay. And halt the production of ATP. I might just take a miss on this one. I don't know what he's explaining here.
Maybe he's telling us that the MCAT would like us to know this relative order of acidity, but in reality, there's a range that could skew with the numbers.
Okay. All right. So, yeah, I guess the way to think about this is when you're thinking about the ETC, just know that the pH of the intermembrane space is really low. The pH of the mitochondrial matrix is really high. So if they're asking you about cytosol, it's safe to say it's just in the middle, because the movement of protons is supposed to be from the intermembrane space to the mitochondrial matrix. Okay, next question. Question number 8. From where does the reactive oxygen species known as superoxide anion originate? As a malfunction of the electron transport chain and oxidative phosphorylation, exogenous sources only, as a naturally occurring byproduct of multiple body processes, or as a product of superoxide dismutase. Superoxide dismutase, I think, is what is an antioxidant that destroys superoxide anions.
Yeah, we have two enzymes that work in conjunction, and the first would be SOD, the superoxide dismutase, and the second that picks up on, I think SOD produces hydrogen peroxide, H2O2, which is easily, since it's a peroxide, easily degraded by catalase into like O2 and H2, or water and H2 or something along those lines.
I would think that okay, so a malfunction of the electron transport chain, that doesn't feel right to me, because yeah, I don't like that answer. Exogenous sources only, I only don't like that because I know that we create free radicals all the time. We create reactive oxygen species as a part of our cellular machinery. So I'm going to say it's a naturally occurring byproduct of multiple body processes.
I agree with you.
And we got it right. Okay, very cool.
That exogenous sources only also pigeonholes you.
Yeah, only is a keyword to look for there, because it's probably wrong.
And knowing that we need to eat things like tomatoes and things like that, like naturally, we need antioxidants.
Right. Okay, very cool. Next question, question number 9. What is the approximate total yield of ATP that is produced via the Krebs cycle and subsequent oxidative phosphorylation of a single molecule of acetyl-CoA? 10, 32, 20, or 16. The total yield of ATP produced in the Krebs cycle, and then subsequent oxidative phosphorylation of a single molecule of acetyl-CoA. Okay, so you said a number. So how many NADHs are produced from the Krebs cycle?
Oh, I couldn't tell you anymore.
I'm going to say 8. I'm going to say it's 2 FADH2s.
Well, one of them is a flat GTP.
Yeah. I'm just pulling numbers out of my butt, and I'm going to roll with it and see if I get an answer. Okay. So the currently accepted science in this room is that there are 8 NADHs produced in the Krebs cycle. That would mean 8 times 3, because every single NADH creates 3 ATP. So 8 times 3 is 24. So 24 ATP from that. And then if every FADH2 produces 2 ATP, according to the MCAT, then it would be 2 times 2 is 4. So that's, what was that, 24 plus 4, 28 now. And that is not an answer, but 32 is kind of close, so I'm going to pick it, and it's not right. The correct answer was, in fact, 10. But why, Con? I'm curious. Why? Let's look at those hints.
This is some hand-wavy science if I've ever seen it.
Okay, it is important to remember that carbohydrate metabolism and cellular respiration are imperfect processes. The number of protons shuttled to the intermembrane space is dependent on what energy level the electrons enter the electron transport chain. Okay, that's NADH versus FADH2, the 3 versus 2 thing. The energy needed to synthesize one molecule of ATP requires 4 protons. Under ideal conditions, 10 protons are shuttled into the intermembrane space per NADH and 6 per FADH2. A single molecule of acetyl-CoA yields 1 ATP, 3 NADH, and 1 FADH2. Okay, so I overestimated a bit. So at this point, without moving forward, I know that so if we have 3 NADH and 1 FADH2, then it's 3 times 3, 9, and then 1 times 2 is 11. Ooh, but that doesn't make sense because they said 10. Let's move forward in those hints. Ooh, that is some math. Okay, so they're doing the protons thing. So for every NADH, you're making 10 protons. For every FADH2, you're making 6 protons. So if you have 3 NADHs, you are making 3 times 10 protons moved into the intermembrane space, so that's 30. But it takes 4 protons to make 1 ATP. So with our NADH, our 3 NADH coming out of the Krebs cycle, we have 30 protons in the intermembrane space. From our 1 FADH2, we can make 6 protons because it's a lower energy state. So we now have 36 protons in the intermembrane space, but remember we can only make 1 ATP for every 4 protons. So that's 9. But the Krebs cycle also makes 1 ATP. So that's 10. Whew.
So
that was some math.
It's really 10 ATP equivalents because what it throws out is really a GTP, but I'll let it go.
Okay, so that's the real takeaway from this question is that every NADH moves 10 protons. Every FADH2 moves 6 protons. And then the Krebs cycle produces 1 FADH2, 3 NADH, and 1 ATP or ATP equivalent to produce 10 ATP for this question. Very cool. Last question. How many molecules of oxygen are required to complete the reactions of aerobic respiration beginning with 4 molecules of glucose? Okay, so if we are doing glucose, we're going to be producing, so for every 1 molecule of glucose, we produce 2 NADHs from glycolysis for every 1 molecule of glucose. Mm-hmm. I think it's 2 NADHs, so that means for every 1 molecule of glucose, you're getting 20 protons, and or no, let's think about it in terms of electrons. So that's 4. We have 4 molecules of glucose, and we get 2 per glucose, so 8 NADHs. You put those NADHs on the electron transport chain, and okay, these are multiples of 8 with the answer choices being 24, 16, 4, or 6. I'm going to go with my gut on 16. Ooh, not quite. Try again. The answer is 24. Okay, let's look at these hints. All right, aerobic respiration is the process of converting organic nutrients into biochemical energy, ATP, in organisms which are capable of utilizing oxygen. With glucose as the initial reactant, this process entails glycolysis, pyruvate oxidation, the Krebs cycle, and the electron transport chain, or oxidative phosphorylation. In other words, it's the complete degradation of glucose.
So I started writing out this equation because I was thinking back to Bio 1, and it's what it made me think of immediately. It has been so many years that I got 6O2 plus written down, and that's it. So there's that.
Okay, so
and that's not even the right.
So they wrote down this equation C6H12O6, which is glucose, plus O2 yields how many CO2s plus how many H2Os plus energy. Okay, so they filled it in that C6H12O6 plus 6 O2s yields 6 CO2s plus 6 H2Os. So 24 molecules of oxygen are required to complete the to complete the reactions of aerobic respiration of 4 molecules of glucose. Okay, so this is 1 molecule of glucose, and you see that it's 6 molecules when you balance out the equation. Okay, so you do that 4 times, 24.
Perfect.
Ooh, okay, going back to Gen Chem, and we balance out our reaction.
Yeah, and it might actually be helpful. I wasn't even thinking to look over something as simple as this, but I mean, it's important, right? They could totally ask you a ratio of the overall thing that drives metabolism is what do we take in, what do we release? You know, we have all these different reasons why, we have all these complicated little background stories for how, but, you know, the overall reaction is really important.
Yeah, and it's a combustion reaction that they're drawing out here. So always remember that for 1 glucose, you're combusting it. So C6H12O6, you're adding so many oxygens to yield so many CO2s and so many H2Os, and it looks like it's an even increase. Whatever coefficient you put in front of one, you're going to put in front of the others. So that will tell you how many molecules of oxygen are required per glucose to fully oxidize the glucose and yank all of the energy that you can from it.
Well said.
Strong work.